Good morning, class, or good afternoon, whatever time you're listening to this video. Welcome to Lesson 7.5, Investigating Properties of the Circle. So last day we did some terminology and learned how to make some calculations of segments and arcs and central angles. Today we're going to focus a little bit more on some of the geometry aspect of it in terms of equal distance and things that are equal in length. So I'm going to be specifically dealing with about 8 different properties, and it says these properties can be stated in different ways. What matters is remembering the situations involved. Okay, so I'm not really too worried if you can't recreate the situation. However, you may have a word problem where they ask you to create it, but just being able to recognize, a mirror image or lines of symmetry, etc., or what perpendicular bisectors do. But let's get started anyway. So there's 8 of them. We'll start with the first one here. Okay, looking at this diagram here, folks, it says chords in a circle that are equidistant from the center of the circle are equal in length. Okay, so if you have 2 chords anywhere on that circle that are equal distance from the center of the circle, then you're going to have those chords being equal in length. There's another way you can express this as well. So it can also be stated as chords of equal length are equal distance from the center of the circle. So the things to remember is that when you've got equal chords, they're going to be equidistant from the center. Okay? Or if they're equidistant from the center, the chords are going to be equal in length. All right, let's take a look at the second one. Number 2, a line from the center of the circle that is perpendicular to a chord bisects the chord. So it's basically a perpendicular bisector. Okay, so it doesn't matter wherever you have a chord, ladies and gentlemen. If you take a line and bisect it, that means you're going to, from the center of the circle out, you're going to make a 90-degree angle, which is right here. And B, you're going to have equal distance, which is marked by these 2 tags, meaning equal in length. Okay, to state this another way, it's the perpendicular bisector. Of a chord goes through the center of the circle. Okay. All right, there's property 2. Number 3. Oh, we talked about this yesterday. The tangent. A line that is perpendicular to the endpoint of the radius of a circle is the tangent on the tangent to the circle. I'm just going to move this. Oh, sorry, my computer decided to freeze on me. So sorry for that jump. The line, so we're taking a look at a tangent, ladies and gentlemen. So whenever you have a tangent, remember that it's going to make 90 degrees with the radius. Okay? Another way to state that, folks, is the tangent of a circle, or a tangent of a circle is perpendicular to the radius of a circle. Good. 3 down. Let's keep moving. I'll flip to the next page. Number 4. 2 tangents can be drawn to a circle from a point outside. So let's pretend this is point A. Okay. These 2 tangents are equal in length. Remember that in the center here, we've got our center of our circle, and each of these are going to be radius of equal length. Okay. If you notice, folks, again, mirror imaging here. So if I was to, let's see if I can do this snazzy way. Let's see if this will work. Come on. Let's see if it works. So Notice there, guys, it's like a mirror image. Okay, so that's why they're going to be equal in length. Okay, just want to see if I can extend that a little less so I can write. Okay. All right, so any questions on that, folks? Okay, to state that another way is that it says two tangents can be drawn to a circle from a point outside the circle. You could say a plane outside joining two tangents. Okay, a point outside the circle joining two tangents will be equal in length. When I mean equal in length, I mean the two tangents. All right. Any questions there, folks? All right. Number 5, an inscribed angle subtended by the diameter of a right triangle. So first of all, the black part here is the diameter. And then if we take both of those and extend in the blue over here, ladies and gentlemen, we are going to create a right angle. It doesn't matter what angle I choose, ladies and gentlemen. So if I go like this and like this, notice it's still at 90 degrees. Doesn't matter where I go. You guys see that it's still going to be 90 degrees because it's going right through the center of the circle. And I can do it on the other side as well. Let's see if I can be creative and get some other colors going here. Let's see. So I could even do something like, oh, come on, please, color. Let's back that up. See if it'll do it for me. Do you think I can get some purple going here right now? Okay? So it doesn't matter. All you need to know is that if the inscribed angle extends from the diameter ends, then you are going to have a 90-degree angle. Okay? Pretty cool, eh? And you could take, if you had a triangle, you could actually shift that around. If it was, if you were using Geometry Sketchpad, you could have a triangle and it could shift it all the way around. So if you're good with Geometry Sketchpad, get on there and try doing that and see if you can have that as a display. All right, number 6, moving along. If two angles are inscribed by the same chord and are on the same side of the chord, the angles are equal. So for example, if we take this blue chord here, ladies and gentlemen, I'm just going to move this up. So if we take the blue chord here and we subtend or extend the where these two ends would meet, okay? So we do it on the red and then we do it on the black. Okay? These angles will meet and these two will be equal. What I mean by that is that this theta or this inscribed angle will be the same as that. Be careful, folks. Will not be the same on the other side. Okay, not the other one on this side. Not the other one on this side. So they have to be on the same sides, okay, guys? All right? Cool. So again, I could use some... Oh, do you think I could get my purple going again? Let's see if I can be creative here. So if I chose to do something like this, okay, and then did the same thing over here, with straight lines, guess what? This theta would be the same as this theta. Okay? And again, if you want to think about it, ladies and gentlemen, it does develop a kind of a mirror image, okay? So, if we take a look, if I can do this right. Oops, I gotta shift it over. Okay, do you guys see that? That's like a mirror image, so that's why those two angles are going to be the same. All right, keep moving along. Two more, guys. We're almost there. All right. 7. Equal chords subtended equal central angles are equal and equal inscribed angles. So that's a lot of words in there. So first of all, equal chords. So if we take a look, I'm just going to put them in red here. Okay. So if you take equal chords, and then you take equal central angles, which are your thetas, okay, and you subtend them to the inscribed angle, then the blue parts will be the same. Again, it's just a mirror imaging, guys, so if you think about that, I don't need you to remember philosophy-wise all that wording. I just need you to recognize that, hey, if I draw a mirror image in here, you could tell that they're going to be the same, okay? So that's what you have with inscribed angles. It also works the same with what we call central angles, okay? So I could do the same thing here by, hopefully, going like this, okay? So again, look at that mirror imaging, okay, to help you with that, okay? The central angles, instead of having a chord, you're just using a radius, okay, or two radii. All right, last one, number 8. If a central angle and an inscribed angle are subtended by the same chord on the same side of the chord, it always has to be on the same side of the chords when you're dealing with that stuff, the central angle is twice that of the inscribed angle. So we're going to do an example of this in a second, okay? But let's start with the basic chord, so blue chord, okay? All right. And we're going to have what's called the central angle, which is in red, and the, my apologies, folks, and the inscribed angle, which is in the green. Notice they have the same endpoints. Please notice that these are two isosceles triangles, right? Okay, so properties of that are going to be that, if you think about similarity, ladies and gentlemen, if I just take the inscribed angle and pull it up to the green, you're going to notice that it's going to be it's going to be stretched, stretched by 2. Okay, so that's why the central angle is twice as much as the inscribed angle. All right, so for further explanation on those 8, please take a look in your textbook, page 148 and 149 as a summary of these concepts. I'll ask you to come back and review that just before your unit test. Let's try one example before we go. All right, and it's dealing with that last philosophy about the central angle and the inscribed angle. So the radius of a circle is 15 centimeters, so I'll put that on here. 15 centimeters and 15 centimeters. The length of the chord AB is 20 centimeters, so I'll put down 20 centimeters for that. Okay, determine the measure of angle ACB. So we want to find this angle right here. So what we notice, folks, is that most of our information is in triangle OAB. Okay, do we have enough information in triangle ACB? Not yet. Okay, so we're going to do some things. And there's 2 ways you can solve this. Okay, and I'll show you both. But don't forget, folks, you got to develop a plan. How would you solve this? Okay, again, trigonometry is going to come into play here if you haven't recognized that already. Okay, so here's my solution 1. I'm going to show you 2. Solution 1. I'm going to recognize, ladies and gentlemen, in triangle OAP, or sorry, OAB, I've got enough measurements here to find some angles. So I've got 15 centimeters, 15 centimeters, and 20 centimeters. Okay, and if I can find angle O using which trig identity, folks? Hopefully you're going to use the cosine law because you've got side, side, side there. And if I find the central angle, I know it's got to be what? Twice as much as the inscribed angle. So what do I know? I know that angle O equals half. Let me just make sure I'm writing this down right. So angle O, yes, is twice, actually 2 times. Angle O is 2 times angle C that we're trying to find. So as soon as I can find O, I can take it and as soon as I find O, I can then find, I back that up. So I erase that. As soon as I find angle O, I need to divide it by 2 to find angle C, the one that we're trying to find. Okay, so I'll just write that out. I apologize. That's twice I messed that up. So angle O, not theta. So angle O equals 2 times angle C. Okay. Therefore, angle C, this is why I was having trouble here, equals angle O divided by 2. So let's find that angle O. And if you don't remember, I'll help you with that formula. So cos theta equals, again, using your cosine law, 15 squared, which plus 15 squared, which are your adjacent sides, subtract your opposite side, all divided by 2 times the 2 adjacent sides. Woohoo, getting ready for the year-end exam. Remember this stuff? Okay, now we're going to find the angle. So to find the angle, we got to take the cos inverse. And let's find your numerator first. So plug that all in your calculator. 15 squared plus 15 squared minus 20 squared. And you should get 50. And on the denominator, 2 times 15 times 15, you should get 450. Please double check, ladies and gentlemen, that your calculator is in degree mode, because I know if you haven't been looking at that lately, it could have slipped into different modes. So I'm going to get here for angle O. Sorry, my fault. I should have angle O instead of theta. Actually, you're okay with that, folks? I'll just let that be theta for now. Okay, so theta equals, plugging that in your calculator, you should have 83.6. Okay, I'm not going to round that yet, ladies and gentlemen, because that's not my final answer. So don't round that angle yet. Now we got to replay it or relate it to this. Okay, so what do we know now? We know that angle C equals angle O, or theta, whichever you want to talk about it, divided by 2. So angle C equals, take that, divide by 2, 41.8 degrees. So angle C equals approximately 42 degrees. So that's method 1, using the cosine law. Okay, I'm going to move this down so I can show you method 2, hopefully. Just give me a second. These take a little longer than I expected. All right, so solution 2, I'm going to add some things to the graph. So I'm going to do a little magic work. Okay, so for solution 2, I am going to drop a perpendicular bisector to this chord, like that. Okay, so my plan here is to create a perpendicular bisector. Of the chord. Okay, and so I'm going to have what's called a 90-degree angle, or a right triangle. Okay, and then I'm going to remember that if I call this beta, let's make it a different letter here, beta, which is really half of this angle I calculated up here, okay, then it's going to equal, so angle beta will equal angle C. I'm going to use beta, so there's going to be a little tail on it, as opposed to angle B, so you're confused. So I'm using this triangle right here, guys. Okay. All right. So based on that triangle, what information do I know? I know that this is 15 centimeters. When I cut 20 in half, I know that's 10 centimeters. Okay. And based on this angle, folks, what 2 sides do I have? Again, go across. I have my opposite, and then I have my hypotenuse. So using SOHCAHTOA, because it's 90 degrees, folks, that's the sine. So sine of beta equals opposite, which is 10, over hypotenuse, which is 15. To find the angle beta, you've got to use the sine inverse of 10 over 15. Okay. Plugged it in your calculator, folks, and angle beta would equal 41.8 degrees. And remember that since angle beta equals angle C, therefore angle C equals 41.8 degrees. And then you can round it to approximately 42 degrees. All right. So since that was a word problem, there's your answer. Oh, that's a different answer there. Okay, so we'll leave that there. I have no idea what that was from. So what we'll do, ladies and gentlemen, is we'll do their first statement. Okay, so therefore angle, how'd they say it? ACB? Angle ACB equals 42 degrees. All right. You know what? I don't even know why that's incorrect. I'm gonna get rid of that. Let's see if I can delete it. I think it's gonna let me delete it. Okay. Anyway, that's a bad calculation because they've used a different measurement there. All right. I would like to delete. Properties, lock, unlock. I don't know, folks. Just please ignore that. All right. So, ladies and gentlemen, apologize for that. Here is your homework. Page 150 to 151, numbers 1A, 2A, 3A, 4A, 5, 6, and 16. Have a great day.